Hello and welcome to another LeetCode video. Today we're going to be doing problem number 207, the problem of the day for July 13th, and it's going to be course schedule. And in this problem you're given num courses that you have to take labeled from 0 to num courses minus 1. You're given an array of prerequisites where prerequisites I, A, B indicates that you must take course B if you want to take course A. So the pair 0, 1 indicates you have to take course 1 before you have to take course 0. Return true if you can finish all the courses, otherwise return false. So let's take a look at the examples. In the first thing, there are 2 courses, and so you need to take course 0 before you take course 1. So that's pretty straightforward, right? You take course 0, then you take course 1, so we can complete it. And now in the second example, we have course 1, we have course 0, and they are prerequisite for each other. And so here we actually have a loop. And so whenever you have a loop in your courses, you're never going to have a solution. So that's one thing to recognize is whenever you have a loop of courses, there are all prerequisites for each other. And so that's going to be the crux of this problem. We're essentially saying we can take courses, but once we are into a loop, we have a no solution. So how are we going to solve this problem? Well, it's actually going to be it's a LeetCode algorithm that you're going to want to be familiar with called Kahn's topological sort. And so in this algorithm, essentially, I'm going to go over what it does. So I'm going to actually show an example here. We're going to draw out something, and I'm going to explain what it means, and then essentially, how you're using this algorithm. Okay, so I'm going to draw out some nodes. So we're going to have node 1, and an arrow means you need to take that course before you take the next one. So we're going to have node 2, and then we're going to have node 3, node 4, and here it's like this, right? So I'm going to draw out a cycle. So you can see there is a cycle in this graph. And then we're going to have 5. It's going to go like this. 6. Okay. So essentially, just to explain what this graph is, so course 1 is a prereq for course 2, and then every single edge means that course is a prereq for something else. So 6 is a prereq for 5, 5 is a prereq for 3. I think this is a little bit easier than an array. Okay? So what we're going to first start out doing is in this topological sort algorithm is we're going to have an in degrees array. And essentially what that's going to do is it's going to give a count of how many edges go into each course. And so this is 1, 2, 3, 4, 5, 6. So these are going to be 0 index essentially. So this one would be at index 0 and so on. So let's take a look at 1. So 1 has 0 edges coming into it. So that's going to be 0 edges. Now 2 has 1 edge, 2 edges coming into it, so it's going to have 2 edges. Now 3 has 1, 2 edges coming into it, so it's going to have 2 edges. 4 has 1 edge coming into it. 5 has 1 edge coming into it, and 6 has no edges coming into it. So what you can recognize in this is that every single node with 0 edges coming into it is like a class with no prerequisites. So those are going to be available to take. Okay, so right away we can obviously take. We're going to actually draw these with a different color. So we can obviously take things with the 0 integers. That's going to be this one and this one here, right? This 1 and the 6. And either one's first. It doesn't matter which one you take first. They're going to lead to the same exact result. So what we are actually going to do is we're actually going to put these into a list. And then we're going to be taking those. And then every time we take those, we're going to delete the edges coming from those. Because it's essentially saying, like, let's say you need to take Calc 1 before you take Calc 2. If you took Calc 1, now that prereq for Calc 2, one of those prereqs is gone. So that's essentially what we're doing. Is once you take a course, if that course is a prereq for another course, we can delete that edge because we no longer need that prereq. It's already been satisfied. So let's take a look what that's going to look like. So we're going to have, and by the way, we can easily build up this whole thing just by traversing the array of edges, right? We're just going to build this up in a dictionary. So we're going to have a list of every node with index 0. So it's going to be node 1, node 6. Okay, now we're going to just be popping from the list. We can pop from the back. We can pop from the front. Doesn't really matter. So we're going to pop node 6. And what's going to happen is we're going to, every single edge that node 6, that comes out of node 6, we're going to actually get rid of. Okay? So what comes out of node 6? This edge right here. And the way we're going to symbolize getting rid of this edge is we're actually going to take the in degrees of whatever node that's going to and subtract by 1. So this 5 had 1 in degree, but now it's actually going to be 0 in degrees, right? So let's actually change that to a 0. It's going to be 0 in degrees. Okay. Now, because that 5 has 0 in degrees now what can we do? Well, we can actually add the 5 into our list because the 5, so we're going to say if something got changed to 0 in degrees, then let's add that into our list. So we pop the 6, but now we're going to add the 5. So now our list is going to be 1, 5. And we got rid of all edges from 6, so we're done with 6. Now we're going to pop 5. And we're going to keep doing this while we still have nodes to pop in our list. So we're going to pop 5 here. Now we're going to look, okay, 5 was already, the in degree 0. Now we're going to take every single edge that came from 5 and we're going to get rid of that. So that's this edge here. So node 3 is going to have 1 less in degree. And so let's do that as well, right? So we're going to take this node 3. It had 2. Now let's delete that. Now it will have 1. Okay. And now let's see what happens with this node 3, right? So this node 3 is not an in degree 0 node, so we can't put that into the queue. It still has an edge, right? It still has an edge coming into it, so we can't put that into the queue. So now we have, or it's not a queue, it's just a list. So now we only have 1 left. So we're going to pop this 1 over here, and we're going to do the same thing. We're going to get rid of that edge, so we're going to get rid of this edge. And for 2, we're going to subtract an edge now, right? So we are going to do that. So for this 2, we're going to subtract an edge. This is going to be 1 here now. And now we have no more queue, right? So our queue here is empty. And these nodes, because they have a cycle, they still have in degrees. This is node 2, node 3, node 4. They still have a cycle, so they still have in degrees. So once our queue is empty, all we have to do is just check through the in degrees. And if there's any node with in degree 1 or more, that means we had a cycle and we don't have a solution. And so it's pretty straightforward. You keep removing edges from all the nodes that have no parents. And then once you have nothing left in your list, all of these should be 0 or you have a cycle. And so if we did get rid of, let's say we never had an edge like this edge. Let's say this edge never existed. Now this would have worked because this would have no in degrees. We'd be able to get rid of this edge. Now this would have no in degrees. We'd be able to get rid of this edge. Now this would have no in degrees. And now every single node would have in degree 0. But in our example, that's not the case. So that's how const topological sort is. You have this list of in degrees, and you have a list of paths, and you just go through your stuff. And while your list is not empty, you keep updating the in degrees, and every time an in degrees turns to 0, you don't really need a visited set because a number in the in degrees can only turn to 0 one time, and that's when you put it into your list. Okay, and so you need to do that, and then at the very end, you just check your in degrees, and if there's anything with a 1 or more, then we have a no solution. So that's basically how the algorithm is going to be, and let's try to code that up now. Okay, so pretty straightforward algorithm, right? So what we need to do we need to pre-process the data to make this graph. So let's do that first. So let's just say paths equals default dict, right? List, pretty straightforward. Now what else do we need? We need in degrees, and that's just going to be n length, so actually num courses. We're going to default it to 0, but we're going to add to it as we go through the paths. So num courses. Now we're going to say for child parent in prereqs. So that's pretty straightforward. Then we're going to say, let's up the in degrees of the child. The child is going to go up by 1. And let's also add the child to the parent list in the dictionary. So paths parent dot append child. So essentially the parent is going to be the node that the edges are coming from, and the child is going to be all of the edges that are coming from there. So now that we pre-processed our data, what we need to do next is we need to make one thing, right? So we need to make a courses or something array. Pretty straightforward. We need to make a courses array. And so let's do that. So for our courses array, what we need to do is we need to actually go through the in degrees, and everything with an in degree of 0, we need to put into our courses array. So for I, v, and enumerate, that's going to be in degrees. Pretty straightforward. Let's actually add these things into the courses array. So if v equals 0, let's add append the index. Okay, now we have that. So now in our courses array, we have everything with 0 in degrees. Now our next step is we're just going to keep looping through this courses array until it's empty. So while courses, we're going to pop children. So we're going to say like cur class equals courses dot pop. And then what we need to do is for, what's this going to be? So for like children maybe, or for child in paths per class. Pretty straightforward. If the in-degrees of the child is equal to 0, then we need to add that into our courses, right? So courses dot append child. So pretty straightforward. And now so once we're actually done with this, that's going to be our whole recursive like loop. Not recursive, it's going to be our loop to keep updating the courses. Now we just simply need to say return max in degrees equals 0, because we're going to check through the in degrees, and all of them should be 0 if we were able to get through every class. So let's just see if that works. Let's see, in digress. Okay, I think actually this should be this. Let's see. Okay, nice. So that actually did work. And so yeah, this is actually really similar to yesterday's problem. It was also a consolve logical sort. It's a rare algorithm, but a definitely good to know one. So now let's go through the time and space complexity. So for the time and the space, let's think about this. So we went through every single prereq, which is O of n. Let's call that length of prereqs. And now so it's basically going to be O of n, where n is the length of prereqs, because we can only put a child into our courses one time. And so the most children that are going to be in here is n. And so this is O of n. Is this O of n? No, this part is actually not O of n. So this part is actually, so assuming these are like an edge, let's call these an edge. This is going to be O of e, where however many edges we have, right? So this is going to be O of e. And let's say the actual course is a vertex. It's going to be O of e plus v, essentially, because for child, parent, and prereqs, like technically a parent can have multiple children. So worst case scenario, like every node is connected to every other node, which would be, a lot bigger than e or than v. So let's call e the length of prereqs, and let's call v the num courses. And so here we're only going to put a course into the courses one time. So that's going to be v. But then we can also go through all the children, so that's going to be e. So it's going to be e plus v, where e is the length of prereqs and v is the length of num courses. Okay, now for the space, let's think about that. So this dictionary is going to be length e as well, right? Because this holds every edges, which is going to be length prereqs here, right? And for every single prereq, there's going to be an edge, and we're going to put that into a dictionary. So that's e. And then this courses can hold every single course, and the in-degrees can hold every single course, which would be v, if v is the number of courses. So it's the same thing. So the time is e plus v, and the space is e plus v. All right, so that's actually going to be it for this problem. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I will see you in the next one. Thanks for watching.